Hey YouTube, the following is part 1 of Andrew Regner's 4-part Tech Talk series on the OSI model. Enjoy.
So this is a rehash of my initial OSI Layer 1 Tech Talk, talking about the physical layer. This diagram here that we're looking at, or just a refresher for anybody who's familiar with the OSI model, defines multiple different layers of the networking stack, which applies to every single networking technology you will ever see. So here at the physical layer, it's responsible for actual transmitting of some sort of a representation of data across a physical medium. That physical medium may also be a radio wave or a microwave or something like that, wireless, and may actually not be tangible, but it is something that transmits data from one point to another. And just to, I guess, set the stage here, for this discussion, I'm not doing any sort of slides, or just going to be talking about pretty things and articles on the internet and stuff like that, just pointing out different bits of the physical layer. So Wikipedia has a very extensive and very nerdy article about all the different physical layer technologies that Wikipedians have cataloged here. One thing I'll point out in it is the list of different protocols that are involved in it. So that includes familiar things that people in desktop and server computing are aware of, like 100 base TX and gigabit Ethernet and stuff like that. But even like GSM used in your cell phone, ISDN, and IEEE 1394, which is otherwise known as FireWire. Bluetooth is a physical layer technology. USB is a physical layer technology. And even modems are a physical layer technology. Modem is a modulator-demodulator, so its entire purpose in life is to modulate one physical layer signaling medium on one end and remodulate it on the other end as a different layer, as a different type of physical layer technology. And all of these physical things are capable of, they're constrained by whatever physical medium they're in. They're constrained by a clock rate of a processor in there, and that will lead to a specific bit rate that it's capable of. So here on the lower narrow band, as they call it, modems have various bit rates in the kilobits per second, which is all just a function of the clock rate that the modem operates at and how many different symbols or how many different representations of ones and zeros it can make with different frequencies of sound over a phone line. And then we get to more digital technologies and not translating something to an analog like a phone line. Then you get into higher bit rates, into millions of bits per second. So it's millions of ones and zeros per second that it's able to push down some sort of a physical medium, all the way up to maybe like an optical technology where you've got billions, hundreds of billions of signals that it can send per second over an optical carrier, all just different types of waves over a different medium. One of those early ones, we'll talk about a few of the early technologies used in physical layer networking. One of those early ones would be token ring, which is essentially that you have these MAUs, which are devices that your nodes would plug into, and you daisy chain them all together and plug in all of your different nodes within it. And then within a single MAU, it has a ring internally to it, so that you see 3 ports in a line, but it's actually just a cycle. And the technology literally works by having a signal or a connection going from one host to the next, to the next, to the next, and back to the first. And the upper layers in the networking stack, like at layer 2, allows it to say, you can talk, and now you can talk, and now you can talk, and so on and so forth. And so that's how token ring networks physically operate, is they just daisy chain a bunch of things together, and then through that chain they're able to communicate with each other. Moving on to a slightly newer technology, ThickNet was popular for a long time, used in office networking for a lot of stuff. I've even actually seen it as recently as 2005 in some offices in a rural town I may have grown up in. And it's basically a coaxial cable, just like your TV line is on, and you you have a device which is attached to your computer through a serial port or parallel port or whatever at the time, and it literally crimps down and like injects into that coax cable to make a connection. And again, with similar technology to the token ring, it's able to coordinate who's able to talk on that medium, on that coaxial medium at a time. Moving on to a more interesting and modern technology, fiber optics is how a lot of high-end networking will work these days. This is a nice little glamour shot of some fiber optic, specifically LC connectors. You've got each port on here, on each of these switches has two connectors. Excuse me. You got orange and yellow and white connectors here, and one of them is sending, one is receiving. So inside of this is literally a glass tube, essentially, that is flexible to an extent that allows you to have a cable, but it just essentially allows you to shoot a beam of light down it, and it's reflected and refracted all the way down that tube to the other end. And then those transceivers that you see plugged into the switch, if we zoom in on this horrible quality picture a little bit, those are SFPs, which is what allows you to have different types of transceivers in your switch. So this is a Cisco 2900 switch, I think. And it doesn't have fiber optic connections on it necessarily, it just has SFP slots. And that SFP is what bridges the connection between the switch and your physical medium, whatever layer 1 technology you're using. So you can swap out those SFPs with whatever you need in your network.
What are some other types?
So some other types of SFPs or other types of physical mediums you might plug into your switch there. Again, this is something else that Wikipedia is great at enumerating, but there are all sorts of different frequencies and types of fiber optics and optical signals you can send down a fiber optic cable like this. There's multi-mode and single-mode fiber, which is just different frequencies, different ranges of frequencies, rather, of that light. And also different SFPs that are possibly stronger are able to shoot a stronger signal down, which means that you can send it down a longer fiber optic cable. This is an image from a data center, so it's probably only going like a matter of a meter or 3 meters or something like that. But there are some SFPs that are capable of shooting signals down a fiber optic cable that goes hundreds of kilometers. And that's obviously how WAN connections are built.
Are frequencies from the visible light spectrum the only frequencies used, or do they go a little bit on either side?
The question was about if the frequencies are used in the visible light spectrum, and no, actually. Most of the fiber optic frequencies used in most fiber optic SFPs and modules like that are not visible light. Mainly just because you can achieve better reflection in a fiber optic cable with higher frequencies. Actually, we'll see that in a minute. So this is another switch with different modules. These connectors are larger; they're SC form factor. This is typically what you'll see in like a fiber optic patch panel, or in some older fiber optic switching or routing equipment. But it's the same idea. You just got send and receive. And this is a interface card that you would plug into a server or something like that. It looks like it's PCI Express 2X or 4X or something like that. And you'll see there it's a similar connector or similar port as that switch had, but this is actually an XFP port, which is just slightly wider than an SFP. But XFP is a newer modular form factor used on switches and servers and stuff like that, which actually allows you to get up to like 40 and 100 gigabit connections with the correct XFPs plugged into it. But it looks fundamentally, it's just like any other network card. It's just, it has the bit that translates the actual data to a physical medium is abstracted out to a modular device. But everything else of how it would communicate with your server, or how the equivalent of this communicates with the switch, is all the same. This is another glamour shot from a data center, but it shows that you have, again, this is an SC connector, but on whatever type of a connector you're using for your fiber optic connections, you have send and receive. So the little red flare there is obviously the receive side on this connection, because the light is coming from some other device on the other side of this patch panel. And some of the, I'm probably going to get this wrong, but I think it's multi-mode frequencies are visible in the red side of the visible light spectrum. So this obviously is not recommended at all, and this will probably damage your eyesight and goes against all sorts of occupational safety hazards and stuff like that. But if one were so inclined to, and one happened to be working in a networking lab of some major network equipment manufacturer, one might be inclined to troubleshoot your fiber optic connections by looking at it, like just shooting it past the corner of your eye or whatever, and making sure that you have the send side on the correct side of the connector, so you know where you're plugging into. Otherwise, you might have to go back and forth and keep swapping cables and just hope it works.
How come they split it out into two different cables?
They split it out into two different cables because otherwise you would have to deal with interference between light coming in two different directions on there. And actually, we'll talk about that too in different technologies that you can deal with that interference in higher end optics. Taking a detour a little bit from fiber optics, you have in larger scale deployments of networking infrastructure. You obviously, in a city, for example, you obviously have lots of people that want connectivity of whether it's a phone network or a data network or a combination of the two if you're Verizon or something like that. Then you have, one fiber optic cable in your street isn't going to do it. So there are underneath any public infrastructure, there's all sorts of conduits of bundled copper or bundled fiber or whatever, and it's really just a bundle of cables inside of a bundle of cables inside of a bundle of cables. And so in here it's a little bit blurry, but it's each one of these little gold things is probably itself another 12 pairs or 12 bundles of cables all wrapped together.
But you desperately need something for scale.
Yeah, this is obviously an older technology, but I guess an older conduit, because even as big and massive as this looks, it only handles a few hundred connections.
How big is it? What's the diameter of that thing?
The diameter of this, it's sort of hard to tell from the picture, but if I had to guess, maybe about a good 12 inches or so,
Okay.
10 or 12 inches round, including all the rubber shielding around it. But yeah, this is, especially if you live in a more rural town, this is what your phone line goes over underneath the street. And in the early days, before fancy multiplexing technology and stuff like that, which we'll talk about in a minute, you had the ability, like the phone line that plugged into your phone and that you literally picked up and talked to one of those wires on that phone line that is electrically and physically separated all the way out to the phone carrier. So you could follow that one single piece of copper from your handset all the way to the phone company's main substation or whatever, miles and miles away. And people wonder why phone signals are bad, because copper is not so resilient. Speaking of public infrastructure, since I'm talking from a company based in San Antonio, Texas, I thought that this article out of B County, Texas, which is just south of San Antonio, was sort of interesting. This is talking about, from a couple of years ago, how they were laying new fiber optic cable along the street. So every time anybody digs up the road for any reason at all, there's probably going to be somebody that says, hey, I'd like to put some fiber optic conduit there, or I'd just like to put some empty conduit there, and eventually we'll string some fiber through it or something like that. Because fiber is cheap, cables are cheap, and it's really easy to drop a cable on the ground and cover it up in conduit. The labor and the time and the disruption to public infrastructure that it takes to dig up the ground to do all this is the expensive and hard part. And so even at my college, for example, just like any other good college. They're always building and always digging up the ground for new buildings and new parking lots and stuff. So the director of IT services at my college came to talk to us once and said that every single time an excavator touches the ground at RIT, he's right there behind it with a piece of fiber optic cable to lay just in case he needs to run another connection from point A to point B.
Heard a very similar thing around town in Blacksburg. We have a lot of just dark fiber underneath the town waiting to be plugged in and used and waiting for those endpoints to be lit up by carriers.
Right, and dark fiber is just fiber optic cable has been laid in the ground and just isn't plugged into anything yet, so it's literally dark and there's no light going through it yet. But it's there ready for somebody to use, and somebody I'm sure owns it and is ready to charge rent on the signals that you put through it. And so this is a picture of one of the construction vehicles or whatever that they might use along the side of a road to lay that. We're going to look at all sorts of different pieces of equipment meant to lay fiber optic cables or any sort of networking infrastructure in an area, but it's just trolling along the side of the road, digging up a hole, and unspooling a piece of conduit into that hole. So, and in a more metropolitan or more urban environment, that sort of conduit would be like under the sewers, in the sewer system or something like that, under the streets. And this is actually a picture of a cable splicing or a fiber optic cable splicing hut. You'll even see these sometimes if you're in a more rural street. They'll set up little huts. They look like little tiny teepees or tents or whatever right there next to the phone pole, where there might have been a cut in a fiber optic cable or some damage from weather or something like that. And this is like one of those like dark arts that you get all sorts of special training and certifications for, and then go out and work for Verizon and make truckloads of money just splicing together fiber optic cables, because it's not like copper where you can just tie it together or make an electrical connection because it's light and it's glass, and you have to bond that together without diminishing the quality of the light going through it somehow. I have no idea how that works, but it's magic. And this is taking a more personal look at it. This is a picture from the networking closet here in the Blacksburg office. Down here at the bottom is our edge router, you might call it. This is a fiber optic connection coming in from a couple of our ISPs that feed the office here at the Corporate Research Center. And it has fiber optic connections going out to other routers and Ethernet, copper Ethernet for management. And then here are some of the other intermediary routers, some on fiber, some on copper, just based on the tier in which it is in the infrastructure, if it needs that extra bandwidth or reduced latency. And here's the cabinet right next door to that, which we were just looking at. But you see there's sort of hard to see in here, but there's a fiber optic uplink from the cabinet next to it. And then you got copper patches to other switches, which are essentially just creating a tiered network topology. And this is all very nicely cable managed and everything. So this is very typical of any sort of office setting where you've got ports throughout the office that all feed to a patch panel here. And all those ports are numbered with a corresponding number at the patch panel, and then you have these tiny little 3-inch cables plugging in from the patch panel to the actual switch, which makes managing your switches or switching that out if the switch fails or something like that very easy. Tedious, but easy. And then speaking of public conduit and infrastructure, this is the conduit coming in from the street into our building. So it's this plastic conduit just is housing a couple of fiber optic pairs, which plugs into this demultiplexer rather, which is essentially bridging or filtering the raw metropolitan sort of networking technologies that they use, going from building to building or from customer to customer, to a more basic simplified connection that our router here in the office handles.
Looks like in that last picture, a fairly severe angle that the fiber optic cable is taking. What kind of an angle can they sustain without losing data?
It can sustain actually pretty. Again, it depends, I guess, on the type of fiber optic cable, frequencies, and all sort of stuff. But this is actually relatively mild. You probably wouldn't want to have like an entire coil a meter or two long at that tight of an angle, but a crimp or two like that is fine. The cables are actually, with the shielding and stuff around the actual optics of it, is designed to only allow you to crimp it a certain amount before it will either just break or not crimp. So it's a pretty, I guess it'll either work or it doesn't. And it doesn't. If it doesn't work, you just spend another $10 on another cable. But that's relatively common. You still have to, especially for a shorter distance connection like this. It's meant to be maneuvering around network closets and conduits and stuff like that, making connections. So it has to be able to sustain something. I guess it's probably like a 80-degree angle or something like that. And this is just the back of that patch panel that we were looking at with all those little tiny red connectors. So these gray cables are coming in from the different locations throughout the office and plugging into the back of the patch panel. And then there's more patches, more switches, and then down here in the bottom left or bottom right is a server. So speaking, we've, I guess, alluded to a little bit about multiplexing. So there's a technology in fiber optics used in larger scale networks and environments, especially inside those dark fibers we were talking about, called DWDM, dense wave division multiplexing. And that allows you to have SFPs, or whatever modular transmitter you want on each end of your connection, to be speaking whatever frequency of light or fiber optic cable or whatever fiber optic technology it's using, but to make that connection with a multiplexer, which then takes that signal, the actual ones and zeros it's signaling, and then shifts its light, or just repeats it but with a different frequency, so that you can then combines all of those into a single physical connection. So this is what one of those devices, I guess a smaller version of it looks like, but you would have, there's, 20, 30 something pairs of cables here, all of them color coded because they're all on different, or they're all corresponding to different frequencies. And then this little box just takes all of it and modulates it all down to a single connection. So along this one single piece of fiber on the other end, you'll have 40 different frequencies of light coming down that one cable. And so just using fancy mirrors and lenses and stuff like that, and some of the simpler ones. You can also have active DWDM devices, which are allow you to be more resilient or more flexible on each end of it, of what type of light you put in and out, but it actively shifts signals around internally. That's essentially all it's doing. It's just combining frequencies of light and putting it down a single conduit. And that is essentially what you will see in an ISP, for example. Like if you have, like we said, it's hard to get a piece of fiber from Chicago to New York, for example, because it's a long distance and it's hard to get a single conduit laid along that path. So once you do get that, you want to make the most use of it. So you can either charge one person one fee for the use of that fiber optic cable, or you can put a bunch of really expensive DWDM multiplexers on each end of it, and then you can charge 80 people 80 times that price for that one piece of fiber. And ultimately, you can still get the same 10 gigabits, 40 gigabits, whatever, out of each of those pairs of frequencies. So the physical capabilities of that one piece of fiber goes from 40 gigabits to terabits per second, just because of shifting light frequencies. And then Within a data center, they can even use those same technologies. So this is a upper conduit in a data center type environment. So these are probably connecting different rooms together. But inside each of these not so glamorous looking metal and plastic conduits are going to be additional pairs of fiber. So we were talking about how they spread these types of connections, typically fiber optics, throughout a metropolitan area or an urban area or rural roads or whatever. But if you need to make a connection from, say, New York to London, you can't do that with a truck or an excavator. So they have actually specialized boats with just giant spools of fiber optic conduit, and they just drive, or they just go from, or sail from New York to London and drop fiber optic conduit on the ocean floor as it's going. And sometimes when I tell people, like, how does the internet get to London from New York and stuff like that, and I said, well, there's literally a cable that goes across the Atlantic Ocean, and like there really are lots of cables that go across the ocean all over the place, and they all have special names, and they're all really, really expensive if you want to rent a frequency on that connection. So this is a closer picture of one of those actual ships. That is literally just a giant spool of conduit that is unraveled as it's sailing across the ocean. Here's one branded by Alcatel, which I guess is some sort of ISP, probably in California. I don't know. But yeah, it's this boat's entire purpose in life is to bring connectivity to other land masses across the world, which I think is really cool. And so speaking of this undersea internet, this is a really neat picture, and if you just searching along Google image search for like undersea fiber optics, you'll see all sorts of things like this, and I encourage you to go out and do that. But I'll point out some things like this is like a very, like there are probably more than this, but this is just a very simplified overview of some of the undersea connections that we have in this planet. You can obviously tell like there's a lot more coming to and from the United States and going to developing countries like China, more modern countries like Japan and United Kingdom and various other places in Europe. Down here there were some interesting statistics I wanted to point out. The world cable capacity. So the total capacity of every single cable or whatever is in the undersea internet is, according to this, 7.1 terabits. Now, I'm sure this is old data and not relevant, but we'll just talk about it for the purposes of comparison and scale. Out of that 7.1 terabits, 5.7 have been purchased by some ISP or provider to use it. And then out of that used capacity, which is I guess only 2.1 terabits is actually being used by active traffic. 72% of that 2.1 terabits is for the internet, the global internet that we all know. 27% for private networks. So this is like if you're a multinational company, you'll have a private network going between all of your offices and have that running in the same sort of fiber optic connections that the internet itself would be on. And so, like I said, all of these cables all have their own names. Talking like CME 3 is supposedly the longest cable at 39,000 kilometers. And I think the next one here is I wanted to talk more specifically about one of those, the cable called ELBA 1, which is the one and only fiber optic connection to the island of Cuba. So looking at some of the other undersea cables in and around that part of the Caribbean, you'll see up here in the top center here is Florida. So there's lots of connections coming out of Florida. Florida is actually a big internet exchange point. And from there, you've got a connection to the Bahamas. You've got even Turks and Caicos has its own, one of those cables makes a stop there on its way to the Dominican Republic. And here's, I guess that's one of the peninsulas of Mexico or whatever. But Cuba here only has this one connection, being such a big country, but a little bit isolated on its own. That cable, ELBA 1, was actually relatively new. And so when it was brought online in 2013, it was, there's some data out about it. So previously, Cubans only had satellite internet providers. Maybe that satellite provider then turned around and offered dial-up or cable service to across some sort of a land connection, but ultimately the way that Cuba got to the public internet was satellites. And so this is coming from BGP data, which is essentially how different internet networks share information with each other. We'll talk more about that in a future Tech Talk. But you see this little gray blurb here at the end is when that Telefonica, that one cable came on, owned by Telefonica, and how it immediately took over a large portion of the traffic coming in and out of Cuba. And that one cable, that one provider took over almost 40% of all Cuban traffic. And then here are some graphs talking about latency. So here's the average round trip latency from Guadalajara, Mexico to Cuba, which, distance-wise isn't that big of a distance. So if you were to try to compare that to an American equivalent, say the distance between, South Texas and New York City or something like that, how long do you think it takes a person in New York City to ping a server at Rackspace in our DFW data center? Not that long. But because they were stuck with satellite providers, they were getting 600 millisecond latencies. And here from some, I'm not even going to try to pronounce that, city in Brazil, even higher. From Dallas, Texas to Cuba, from Sao Paulo, Brazil to Cuba. But as soon as that Telefonica provided connection came online, you see the average latency is immediately dropping.
It seems like it only dropped by about 200 milliseconds. What's still taking the fiber that long, or is that normal?
It's not normal necessarily, but I guess if you take it in context that to get, if this is obviously incomplete, but if this is your map of physical connections in and out of Cuba, then even if it is going to be going over that, it has to first hit Jamaica, then it has to transit through some sort of Jamaican ISP, and then hit this other line here when it bounces off the Cayman Islands, and then
it's going straight to Brazil.
Whatever. Venezuela. Yeah. So like, if you were trying to get to Texas, for example, Texas is up here, so you'd probably connect to some one of these other connections. It'd probably be routed over a connection over here, and off through some Mexican ISP eventually until it gets to Texas. Or if you're going to Brazil, then you probably hit Venezuela and Caracas here first, and then south through some Venezuelan ISP. So you're still at the mercy of every single ISP between you and your endpoint. If they were doing ping tests to Jamaica, I'm sure it would be a lot quicker. And also, on top of that, not all Cuban traffic immediately went over that same line. It's only a single piece of fiber that only can handle so many gigabits.
Is it what kind of latencies are typical for other fiber, like cross-Atlantic? Do you happen to know off the top of your head? Again, it will vary a lot between network providers and architecture. But if you're pinging a host and you are directly connected to that host by a fiber optic cable across the sea, then your latency is really just the speed of light. So, I don't know off the top of my head what the distance or the time it takes at the speed of light to get to London, but not that long.
Right. I've heard of financial institutions having fiber optic cables spread directly from London to New York, so that they can be 1 to 2 milliseconds faster than their competition and make the trade faster and make billions of dollars.
Yeah, that's exactly right. And there's even technologies that these micro trading computer systems that they use they'll have points of presence in all the different financial markets along the world, just so that that final trade can be executed by that end system in Japan or Hong Kong or London or wherever it is.
Have you heard of any cases where those cables have gotten cut?
Oh yes, lots of times.
The first thing you said when I saw one cable is, "Oh man, that's going to be a crisis when that thing goes down." But
Yeah, it's just like anything else, anything can happen. I'm sure anybody that is at all connected to their local infrastructure is aware of whenever a phone line or a fiber optic cable in your own town gets cut. It can happen just as easily under the sea if you're doing exploration or laying a new cable even and accidentally damage or sever another one. And you just have to either replace it or work around it and let it sit there broken, or you go out there with one of those fiber splicing tents and fix it, which is obviously really difficult in the middle of the Atlantic Ocean.
Yeah.
But
those are pretty deep down there. I
Yeah,
imagine. So
yeah,
it's-
and there are fiber splicing boats even, just like that truck we saw in the middle of that city.
Must be difficult to find the cut unless you can somehow figure out the distance from one of the.
Yeah, and there are technologies actually that you can plug into one end of a fiber optic connection and send a signal down it and see where it degrades, and then estimate within some tolerance of a number of tens or hundreds of miles where to go out and test it.
Wow.
But yeah, whenever actually, I think this diagram here was talking about. I haven't done more research about this. I probably should have, but talking about the number of internet users affected by the Alexandria accident, which I think was one of those undersea cables that was cut, and it happened to be carrying a lot of traffic, and so there was a lot of people affected by it. Obviously, most of them from India, I guess. So if Alexandria is presumably near Egypt. Alexandria, Wednesday. A ship's anchor accidentally cut two cables, CME 4 and FLAG, Europe, Asia, reducing internet capacity in Asia by 75%.
Wow.
So that's exactly what happens. Like that remaining 25% capacity gets overloaded and latencies go up, throughput goes down,
Yep.
etc.
Wow.
Welcome to the internet. It's just as janky and broken as your own home network, but bigger. In the end, it's all just cables. Any other questions? That's all the tabs I have.
We're out of tabs?
We're out of tabs.
Oh.
Did I miss the bit about what frequencies are most typically used?
Oh. Yeah, maybe. I think that was mentioned somewhere in here. Maybe I didn't point it out, but or not. Let's see. Fiber optic frequencies. So you've heard of live coding. This is live researching.
I mean, you typically associate red with things like that, but that's even the lowest frequency for light. So.
Blue cables are multimode fibers, 62.5 over 125 micrometers. Is that a fraction? Fraction of a micrometer. Yeah. Actually, if I do a search for no. So this is talking about the maximum distances at different Ethernet technologies. So if you're going 10 gigabits, you can only go 33 meters. But if you're going 100 megabits, you can go 2 kilometers.
Do you guys have any other questions? Cool. Well, Andrew, thank you for giving this talk. Thank you guys for coming, trying this little experiment. Cool. Yeah, thank you.
Thank you.